In the second part of this lecture, we will show how we can design advanced medical image segmentation methods within a probabilistic framework. We have seen that simple clustering approaches can work in some circumstances. For example, this is the case in adult MRI with low noise, as long as it has been pre-processed properly. And by that, I mean that intensity inhomogeneity has been corrected and the skull has been removed. And also, this is only if we are interested in three classes: white matter, gray matter, and CSF. In this case, Gaussian mixture segmentation performs well, as we have seen, and k-means would also work. But it does not always work. For example, when the data is noisy, the noise will appear in segmentation as well. Or if we need more than 3 labels, if we want to further parcellate the brain, then we will not be able to do it with a simple clustering approach. Or if we choose to segment an object, such as whole fetal body in fetal MRI, the intensities are not uniform. And in this case, this is really difficult to model. So let's now have a look a bit more theoretically at this maximum likelihood approach for segmentation to see how we could further extend it. So the Gaussian mixture model is really just a special case of this maximum likelihood approach. So to see how this can be done, let's see how we can expand this likelihood term. So that's a likelihood of observing certain intensity in the image, irrespective of the class given the model parameters. And what we can do, we can apply the total probability theorem to this probability, to this likelihood. And what we will then get, we get likelihood for each class. So depending on the label k this time, multiplied by the prior probability for this class. So that's the probability of observing this class if we don't know the intensity yet. And we sum up this through all the classes. That will give us the overall likelihood. And now in Gaussian mixture model, we made particular design choices for these likelihood and prior terms. The likelihood term was a Gaussian distribution, I mean likelihood for each class. And the prior for each class was the mixing proportion. So we chose a constant prior. Now we can change these design choices and build more complex models. So for example, we could look at intensities of neighboring voxels to deal with noise, or we can localize more than 3 structures by including spatial prior distributions. So we also need an optimization algorithm for this generalized case, and that is expectation-maximisation algorithm that can do that for us. So it's also called EM algorithm, and it iterates between 2 steps. The first step is E step, or expectation step, and in this step we calculate the probabilistic segmentations. So that's a probability map for each class, and these probability maps are actually called posterior probabilities. So these posterior probabilities are calculated using Bayes formula. So if we apply Bayes formula to this, we will obtain the likelihood that we already know, the prior that we already know, and this denominator is really just to normalize the posterior probabilities over all classes to sum up to 1. So in the M step, or maximization step, we then update the model parameters. And we do that but by maximizing this quantity, this criterion. And you see that in this criterion, we need to use the posterior probabilities, the likelihoods for each class, and the prior probabilities for each class. And from these, we can then calculate the optimal model parameters. So this expression is really a lower bound to the maximum likelihood objective, and it can be used to maximize this objective indirectly. So let's have a look at an example. So, for example, we could correct the intensity inhomogeneity during the segmentation within the EM framework rather than beforehand. So first, what we need to do, we need to design a model for this intensity inhomogeneity. And in MRI, this is a smooth multiplicative field that I denoted here B. And this field is parameterized by some parameters beta, and it also depends on location of the voxel, which we denote UI. So what are these beta? So the field B can be parameterized as a polynomial or through splines. And in this case, the beta would be just the polynomial coefficients or control points of the splines. And here we can see how we apply this model. So if these are the original intensities, xi, once we multiply by this bias field, inhomogeneity field, we want to obtain an image with uniform intensities for each class. So to incorporate this bias field into our model, we will amend the likelihood for each class, which we have modeled using Gaussian distribution. So in this Gaussian distribution, we will multiply the intensities by the bias field, inhomogeneity field. So you see that what we have done, that we now require that the intensity for each class follows the Gaussian distribution after it has been corrected with this multiplicative field. And next step we need to, so this will be incorporated into the expectation step. And we also need to create an equation that we need to optimize to find the parameters beta. And for that, we will use the maximization step. And if we set all our parameters into the expression there, this is the quantity we need to maximize, which will give us objective that we can then use to find the parameters. Let's look at a different example now, and that's when we have a noisy image. So in the previous example, we have amended the likelihood. Now we will amend the prior. So if we just apply Gaussian mixture model to a noisy image, the segmentation will only depend on an intensity of a single voxel, and it is then expected that noise will propagate to the segmentation. So the idea is that we can also look at the neighboring labels, because they are very often the same as the correct label for each pixel. And then we will decrease the prior probability of a certain label if the voxel is surrounded by different labels. So let's have a look how we can do that. So we can do that through Markov random fields. So we said that each label for each voxel would depend on the other labels in the image as well, but that would be too difficult to model. So we will instead require a Markov property. That means that labels will only depend on its first order neighborhood, on the first order neighborhood of the given pixel or voxel. So let's look at the example in 2D. This is our chosen pixel that we're looking at, and we want to find what label that it should have. And to do that, we will look at the labels of its 4 closest neighbors. So then the probability, the prior probability for this label will only depend on labels of the neighbors and not the rest of the labels. Now we need to model this. So we will consider pairs of labels that are also called two cliques, and we will have potential for these pairs of labels. So these pairs will be the voxel I with its neighbor, and with the other neighbor. So in this case, we have 4 pairs, and each of them contains the the central voxel, and one of the neighbors. And we will set this potential to positive number beta if the two labels are different, and to 0 if they are the same. So you see that these potentials really act as penalties, because we try to penalize different labels. And this value beta is a parameter that will control the strength of the penalty and also the strength of the prior as a result. So now we'll need to convert these potentials to prior probability. So first what we'll do, we will sum up these potentials over all the neighborhood, and then we'll take the function e to the minus x out of this sum of potentials. Why do we do that? Because you can see that when potential is 0, we get 1, so we get probability 1. And if the potential is increasing, then this quantity will decrease. So then this will lower the prior probability. And this term here in the denominator is to normalize the prior probabilities over all the classes so that they sum up to 1. So to sum up, a different label in the neighborhood creates a penalty and lowers the prior probability. And if there is the same label, there will be no penalty. But the problem with this is that we don't know the labels in the neighborhood. We try to estimate them at the same time as the label of the central voxel or pixel. So we'll need to find a way to deal with it. And one of the solutions is called mean field approximation. And that just means that we will use posterior probabilities that we have estimated so far rather than labels. And in this case, we will sum up the potentials not only through the neighboring voxels, but also through all the classes, and we will multiply them by the posterior probabilities for that class. So this gives us a tractable solution to the Markov random fields formulation, and it can be incorporated as a special step in EM algorithm. So at each iteration, we will recalculate the prior as well. And here is the result. So here we have the noisy image. This is Gaussian mixture model with noisy segmentation. And after applying Markov random fields, we'll get a nice clean segmentation. However, it comes also with a downside. You can notice that some of the anatomical features were also deleted through this approach. Like, for example, here we lost some true white matter. So this is just a simplest possible example of use of Markov random fields to model the prior, but we can also model more complex relationships, for example, higher order cliques or higher order neighborhoods. Another example how we can change this type of EM segmentation algorithm is to use anatomical priors. So this will be useful in an application, for example, when we require more detailed parcellation of the brain. So we want multiple brain structures. And this cannot be clustered just based on intensity. As you can see here, these are the real distribution from this real data set. And you see that they overlap a lot. So it's impossible to separate these structures based on intensity only. So what we then can do, we can create a probabilistic atlas where we will, which will contain the spatial localizations of each structure. So here you can see such an atlas for just white matter, gray matter, and CSF, but we could include all the other structures as well. And basically, these probability maps will be then set as a prior for the EM segmentations. So how do we obtain these probability maps? So they are usually created by averaging a number of aligned segmented images. They contain the average image, which is called a template, and then the probability maps for each class, and these are created simply by averaging the segmentations. And this probabilistic atlas then needs to be aligned with each new image that we want to segment. And the easiest thing to do is to just register the template with the image. Or we could also include this alignment in EM algorithm, and then we would be able to use also the prior probability maps for the refinement of the alignment. So this is all I wanted to show you from about this kind of framework. But the conclusion to take out of it, that maximum likelihood through EM algorithm is an extremely versatile framework for designing segmentation methods, and it is widely used for segmentation of brain MRI, and these are the famous widely used software packages that implement some versions of this approach. It has been the state of the art until deep learning arrived, and now it's a question whether it still is. I would say that for application of adult brain MRI, it probably will remain a mainstream approach and will not be completely replaced by deep learning. But sometimes this type of modeling can fail completely, and that's when there is really time to reach out to deep learning. And for example, this happens if we are interested in segmenting the whole fetus in fetal MRI. You can see that the whole fetus obviously doesn't have uniform intensity. It's not a region of uniform intensity. There are overlaps with the maternal tissues. We cannot get it just by clustering. And also the position of the fetus may vary a lot within maternal body. So we cannot just simply create a probabilistic atlas of where the baby is going to be. So we really fail with the previous approach for this application. And this is really where convolutional neural networks excel, because they're able to learn complex local and global features, and that way localize the different body parts in the image. And we can then get the segmentations out like this. So if convolutional neural networks are so powerful, do we really need the deep, non-deep learning segmentation methods? So of course, CNNs are powerful because they're able to learn directly from annotated data. They are very versatile because their filters will adapt to applications, and therefore they do not require uniform intensities for different regions that we try to segment. And they are also very fast once they are trained. But there are also disadvantages of using CNNs. We need a lot of training data with manual annotations, and this is often a problem in medical imaging. Because obviously we struggle with the amount of data that we have, and we also struggle with the amount of manual annotation because it's very labor intensive. Secondly, they don't necessarily generalize well to other data sets, such as, for example, if there is a change in acquisition, which results in change in the contrast. This is because CNNs will learn filters that are adapted particularly to the training data set. So it's really tailored features, and these features might not really be applicable to a different contrast. So we always have to keep this in mind. Then the training is time consuming and resource hungry, especially for three-dimensional medical data. We need a very powerful GPU usually to be able to train. And finally, if traditional methods perform well, CNNs do not necessarily do better. We actually often see a slight drop in performance. So that's why I think that we need to approach the segmentation problems in medical imaging with open mind and take advantages of both approaches. For example, it might make sense to use traditional method to create training data for CNNs. And that's all I wanted to tell you today. So next, it's time to complete the quiz on kids that is called probabilistic segmentation. And after that, please watch more in Ben's lecture. This is to expand your knowledge of alternative segmentation methods and also to learn about how we evaluate the quality of segmentation. And we will also teach you more about the deep learning segmentation, and the lecture is coming later in this module.